little mean and lean in the other classes as well? I see. Okay. So let's see. Yeah. So last class I mentioned there were 4 TAs. So we actually have only 3 right now. Rajesh and Fanindra you have seen. Is Timesh here? Timesh will probably join us from Monday onwards. So yeah, this Monday is of course Independence Day. So we'll have the next class again on Friday, and then he will join us on that day. Just see if the signal is going on this as I speak. Okay, so that it's kind of. Thank you. So I found the audio recording was a little weak, so thought of using a wireless mic to see if things are better. You can just tell me, keep a watch over the battery level also. In case the battery goes down, we'll use the regular. Okay, so as I mentioned, we are from the NMCAD lab. So we work mostly on nonlinear problems and multifunctional materials, whereas this course we will be primarily dealing with unifunctional materials, which means load bearing is the primary function. As part of load bearing, of course, it has to offer a certain strength, it has to offer a certain stiffness, it has to offer certain stability. So in that sense, there are various sub-functions within that. But in terms of the overall function, it's essentially load-bearing material. And we will be considering composites right up front in this whole course, which is unusual for a undergrad level course. But I think without that, it will be not of much practical use once you go either to the industry or to academia, wherever, because the composites have become so widely used in aerospace today that without that, it's unthinkable. So it's very, very critical that we understand structural mechanics and flight vehicle structures from the perspective of composites right up front. So while I'll be walking you through, so those of you from EE, EC and other backgrounds don't need to worry. I'll walk you through the steps of introduction to elasticity, but in consideration of composite materials rather than bringing them as an afterthought later on to make things more generalized or correcting them that way. So I think that's the way it probably will work best for everybody. Then we do both analysis and design for various applications, not only in the aerospace industry, but also other allied industries. In the last class, when we were talking about the various differences, one of the things I forgot to mention is that in mechanical engineering, if you look at, or automotive engineering in particular, we saw a few differences, but once you get on to, let's say, you're talking about racing cars like for F1 or even the electric version of that, the kind of materials that are used are almost similar to aerospace, or some cases even beyond that. So they tend to lead the whole bandwagon over there. So it's not that aerospace has always been the pioneers in everything. Wherever money is and wherever the best minds are there, things happen, and these spin-offs go off to the other allied industries. So that's how it's been working, and it's for the betterment of the society as a whole. So I think pretty much we have covered everything. To tell something a little about the department, of course you would have heard from the chair the introduction and other things, but essentially it's an 80-year-old department, so it's very interesting that you are the 80th year batch. So in that sense, you're all special, the MTech students who have joined this year, or any other admits who have happened this particular year into this particular department. And just about 13, 14 years back, we completed the centennial of the institute. So the aerospace department's history has been almost allied with the institute almost from the beginning, and in particular, almost at the same time HAL started, just a year earlier. And we've been catering to the human resources, not only of HAL, but many of you are from ISRO. Yeah, good. DRDO? Okay, anybody from the armed forces? Okay, excellent. So we have had many students from all of these organizations, which are very well known today in India. And some of your top people are all from are alumni from this institute, and the umbilical cords are very long. We continue to maintain very cordial relationships, and many of the national programs, ISC faculty and students and researchers have participated in. So we have a very good practical understanding of what we teach and what we do research on, how it eventually carries over to the real world. So I guess that's pretty much it over here. Let's move on. At the end of the previous class, many of you are asking about the grades and how the grading will be. So this is just an illustration of how it would not be. So there's absolutely nothing to fear. I've already told you, most of you are masters and students and a few PhDs, and of course the undergrads, so 4 of them. But nonetheless, this will be at a level where we are trying to introduce flight vehicles and particular structures to the non-aerospace background people. So in that sense, it's more of an introductory course. So what is more important is the second line of the title here, the takeaways, rather than the grading. Because it's a formal course and you're in a formal degree, obviously we don't have a way to get away from the grading. If I had a choice, I would have perhaps done that, because for me, the learning is far more important, the interactions, the teams that we build, the networks that we build. For example, the kind of classmates I've had in my master's, I did my master's here as well in the same department. We have had wonderful networking, and a lot of projects and collaborations have resulted out of those collaborations not only with the structures people, but also across the streams. And that's what is very critical over here in terms of understanding that what really works in the real world is the teamwork, and the kind of friendships that you build, the camaraderie can translate into professional relationships over the entire career, if or at least a few decades or particular projects, which means that it could benefit not only you as individuals as part of the team, but also whichever organizations that you're working for, and the country, nation, and the science and technology in general. So keeping that in mind, takeaways are the most important part of this. Nonetheless, as I said, we do need to have a few ways of marking you, and the TAs will be a critical part in this whole thing. As and when I feel like during the class or at the end of the class or in the middle of the class, we have reached a certain point where certain possibility of you going exploring a little bit more and trying to add to what has been done in the class. So that is where the assignments will be issued, and these assignments will all have a 1-week turnaround time. So in other words, if I give it on a Monday, then it will be due the next Monday. Unless that's a holiday, then you do have it turned over the Friday. So essentially, most of these are things that you submit online, and though I gave an email address, please don't send those assignments to that email address, because it gets unnecessarily blocked. So as you know, we have a Microsoft team for this particular course. So that's where you submit your assignments, and the grading and the results would also be submitted over that. Is there anybody who has not yet joined the Microsoft team and is still crediting the course? Okay, I guess all of you have joined, so that's good. More or less the assignments would be of the same weightage, but there might be some which are a little more complex. So based on that, we will decide on the relative weightage of the assignments, but eventually they'll all add up to the 50% of the overall marks for the course. We will not have any midterms. Right away, we will go into the final exam. And for all courses, the Institute has declared a calendar according to which 23rd November, I think, is the last class. You'll have about a week of steady leave. And then 30th November to 9th December would be the final exams for all courses. Specifically for this course, which date it will be announced by the Institute based on the class timings. So it's very important that if any of you are having class schedule conflicts, you might have an exam conflict also later on. So don't make the mistake of attending or rather crediting two courses which are held at the same time. You could have issues at the end, as we unfortunately found out in a previous semester. So it's somewhere in between that, and once that is available, you will know, because it will be sent by broadcast. And if I also happen to read it, I will let you know. As I said, the takeaways are the ones which are more important than this grading system that we have. The final exam 50%, again, it will also be something that is more real life oriented, which means that I will not have a final exam which is classroom based, handing out question papers and doing it. It will be more of an extended assignment. In other words, it's just essentially an open book, open notes kind of a thing, and not just limited to 3 hours like typical final exams are, but it could be probably 2 or 3 days. I will mention the exact deadline based on the complexity of the questions that I said. So it's very important that you know that you're doing these things on in the way that it is done in the real life, because when you're working on a particular project, either for the industry or for research in academia or in research labs, you are always having access to the data, information, all these things. There's no need to memorize all of these things, which I find is a very unfortunate thing that is still happening, especially in these days of the internet. You have at your fingertips the access on your smartphones. There's absolutely no point in making somebody memorize certain things and coming and vomiting it over here. It's more of that application that is very, very important. And in that process, what is unfortunately not perceived by many is to unlearn the not so correct. So while there's a lot of emphasis on learning, unless and until you unlearn certain things, what you have already learned, which for various reasons could have been not so correct, unless you unlearn that, there's absolutely no point that in learning something new. It's like putting, let's say, milk into a dirty container. So even the fresh milk that you add will be spoiled. So let me just illustrate a few examples of what I mean by unlearning the not so correct. One very classic example, and many people are surprised to know that, is, and I'm not making it very comprehensive. I see, okay. You can zoom in, still doesn't work, is it? Okay, okay. You can just, because I've not switched on this thing, so, but you might have to hold probably because it will not stand. I have not switched it on. Yeah. Yeah, so what I was saying was, yeah, so I'm not going to talk about various things. I don't know what all you have learned and which of those are incorrect, but some things which I'm very sure many of you, especially who have had inclination towards structures, who have learned a few things and thought that was kind of sacrosanct. Many of these things in the current state of the art have been disproved and mathematically quite rigorously. And one such example is the so-called Timoshenko beam theory. Most of you from strength of materials will be familiar with the simpler version of it called the Euler-Bernoulli engineering beam theory. That is very interestingly fairly valid result. But when you try to improvise on that and go to the next level, Timoshenko beam theory, great person, Steven Timoshenko, highly honored and great achiever, lots of books to his credit, etc. But in this particular beam theory, which is unfortunately continues to be used in various places, including the industry sometimes, there are certain highly erroneous assumptions. And these assumptions are some things that Timoshenko himself actually found out, and which is the reason why he introduced the concept of shear correction factors. So if the theory was quite rigorous, then there would have been no need for these shear correction factors, which are empirical in nature. So these kinds of things then carry over, and just like he developed a theory for beams, which took care of what is known as transverse shear, then two more people called Reisner and Mindlin, again very big names in our community, came up with what is a plate or shell theory, which is along the same lines as the beam theory in terms of its assumptions. So what kind of assumptions it made, and once again they also need to introduce the same thing called the shear correction factors, which is kind of common to both of these methodologies because of the same quality of assumptions that were made. It would be okay at that point of time because there were no alternatives. But today there are lots of alternatives to this whole thing, where you can have what are known as asymptotically correct theories, which are mathematically rigorous, physics-based, and get rid of those assumptions. Because as we shall see in a later class, you need to make assumptions. When you model, you are obviously, the very word modeling means that it is not reality. But when you model, you have to go as close to the reality as is possible or feasible from a practical point of view. Pure academicians would tend to go as close to it, which means a lot more investment in computational and or theoretical analysis, which may not be directly applicable to the industry. That is one end of the spectrum. The other end of the spectrum is people using very, very simplistic theories, which can be worked on your calculator or even at the back of your paper napkin kind of calculations, which are good, again, for a ballpark value to understand overall how it fits in, but eventually when it translates to an actual product, getting it to the market, etc., many of these things fail quite miserably. So what's the point in knowing some of those things which are not of practical relevance anymore, and when there are alternatives, much better alternatives, which work much more efficiently and also give you much more accurate results. So that's the whole idea. So this is just two examples of many, many that we can go on listing, but the idea is that you're trying to unlearn some of those things. And when you unlearn the not so correct, then it opens up the space, your mind space, for new ways of thinking and innovative ways of thinking and seeing how the same problem could be attacked with the current state-of-the-art knowledge. So that is not enough, though. Once you have unlearned the not so correct, obviously you have to learn the more correct. Otherwise, you might as well continue doing what you were doing earlier. So the fact that something more correct exists is what has motivated us to unlearn the not so correct, and then you learn the more correct. And what I'm saying is not just restricted to those. Tomorrow what I teach might become not so correct, and there could be something which comes up which is even better, and then you would have to unlearn what I have taught you and learn the more correct. So what we are talking about is an evolving modeling techniques, the rigorousness of the model from the physics aspect, from the mathematics aspect, and seeing what is the extent to which we can go and still be able to do it in a routine basis, not requiring days on end on a supercomputer in order to achieve your results. It has to be practical on a regular desktop or something, a few hours at the most, or a few minutes if possible. That is the kind of possibility for realistic actual aircraft flying vehicle structures that we need to get into. So again, these two are just not enough. we need to go to the third level where we are trying to actually see how we can apply this to the real life. So one is you have unlearned, you have learned something which is more state of the art, not just for the heck of it being state of the art or modern. It's like fashion. You just try to copy somebody else who is trying to bring something into fashion, and you're trying to aping that. It's not like that. It's because of a particular practical reason that it is better, faster, or cheaper. One of these three, or two of them, or all of them. So that's how things evolve. It's essentially Darwin's theory of evolution, survival of the fittest, in the case of the modeling or in the case of analysis and design as well. So essentially, you're looking at an enhanced ability that you're developing in each one of you to apply that assimilated knowledge. So you might ask, for those from a non-structural background, what is the whole idea of this? It's important for the non-structures people also to learn these newer techniques, because your colleagues in your teams will be using these techniques and will be using certain terminology associated with it. And if you're left wondering what it is, things may not move in the team as a whole. So it's very important that you at least learn the nuances, the concepts, the terminology. We're not going to the depth of all these things. We have a separate course for this called the Nonlinear Mechanics of Composite Structures, which I typically teach in the January semester, where we go into the detailed mathematics of this, the physics behind it, etc. For those of you who are going to specialize in structures, you might consider that. But otherwise, this basic introduction to that is what will happen towards the second half of the semester. So any questions on this? Okay. So let's move on. So next we talk about the textbook. So as I said, we are teaching this at an undergraduate level, so most of the content, not all, will be taken from the Mechanics of Aircraft Structures. It's a 2006 book, about 16 years back, but still most of the things that are said there are relevant today because of the fact that most of these are based on fundamental math, etc. There are certain places where he goes into the same loop as either Timoshenko, Reisner-Mindlin, or etc. We will make corrections at those points in time. But this is a great professor at Purdue University, now emeritus. So C.T. Sun is the second edition of his book in 2006. So that's what we will follow. The library has e-copies of that, so you can access it from our digital library. I'm sorry. Yeah, so these are the chapters in the book. I'm not sure if we'll have the sufficient time in a 45-hour course to cover all of these things, because I would like to do justice. It's not a question of what all you have covered. Rather, whatever you have covered, you have to cover it in a certain way that it's of utility when you go back to wherever you are going to be working in the future. So probably I would say about the first 4 or 5 chapters we would be covering in a certain amount, and the 6, 7, and 8 will be touching upon as not as separate topics, but as and when we cover some of these things, we will include aspects of these over there so that you understand what happens towards the when you push the limits as far as the applicability of these structures are concerned, how they behave, what are the different ways in which damages can set in and it can become unutilizable, or it could be repaired and put back, or it has to be overhauled. All these kinds of things we will touch upon, not as separate topics, but in between. Yeah, so in the previous class, we talked about aircraft materials. So aircraft materials, the characteristics of that, and try to distinguish it from the typical materials which are used in civil engineering and or mechanical engineering, etc. Now we will go into a little more detail of that. I mentioned specific quantities like specific strength, specific stability, etc., specific stiffness. All those things we'll try to get into a little more detail. And then the structure itself. So one thing is the choice of material, but once you have the material, what kind of a structure you design out of it. And here's where there's a big distinction in terms of how we are moving towards today and what we were doing in the past. The past, it was more of a compartmentalized thing, and you're trying to build it up and cover something together. So here, what we are trying to do is to understand it from a more holistic perspective and then try to put things together. To give you a classic example, not structures, but flight vehicles as a whole, if you look at how, let's say, a bird or an insect flies, it's typically by flapping. And this flapping mechanism generates both the required forces for you, which is the lift as well as the thrust, depending upon the way in which it flaps. Birds like hummingbird, etc., can even have a vertical takeoff, vertical climb, and most birds can have different angles of climb, and all of this is just by modifying the wings. So in other words, the source of the lift and the source of the thrust is just the wing of the bird or the insect. But if you look at the way we started off, and most of what we have been doing in human-powered flight, not human-powered in the sense of the human powering it, but essentially engineering-powered kinds of flights, we have separated this right from the time of Wright brothers, where we had the engine providing the thrust and the wing static with respect to the fuselage, except for the vibrations, but that's providing your lift, which means that we have done this specialization. It's very similar to the way Western science in particular has approached all problems. If you look at the medical field also, you have hundreds of specialists for various things, the cardiologist to the ENT specialist to what have you, the rhinologist, etc., etc. And so you're thinking of this human body as various parts. And that's how the overall approach has been to the flight vehicle, both the design as well as the analysis, to look at it as various parts. So if you talk of, let's say, the So you talk of the fuselage, you talk of the wings on the starboard and the port, and then you talk of the horizontal and vertical stabilizers that you have, the vertical tail and the horizontal tail. So you already have divided, and of course the engines, unless it is a glider. And so already you have classified into various parts. And then within each one of them, you look at the various structural components that are associated with it. And those structural components could include what are known as bulkheads or ribs, or it could be the stringers or longerons, it could be the spars, etc. And of course the skin. So we will come into defining each one of these parts a little later on. But purely from the approach point of view, I'm just saying that it's a compartmentalized approach, both in terms of how that is made possible, flight is made possible, and also in terms of analyzing these structures. But unless and until you have an overall understanding of this whole thing, it's you get lost in the details and you don't know where this is going into. And this is very important because you're doing this course on flight and space mechanics. That's what will kind of bridge this gap that is happening because of this way. Because we don't have a better way of doing it at this point in time, at least. It's the standard way of approach across universities, the best universities of the world, and we are typically following a similar kind of a curriculum, and that's what has resulted in this. But FSM is a course which will be able to stitch all these things for you together. The way it will approach, especially in Professor Padi's part of the course, would be talking about this as a rigid body. This whole aircraft has a rigid body where you're having 6 degrees of freedom. So any rigid body, as you know, in a 3-dimensional space has 3 translations and the 3 rotations. In the case of the aircraft, if this is the nose of the fuselage, then you're essentially having the pitching motion, which is coming by deflecting your elevators. Then you are having the rolling motion, which is happening by deflecting what are known as ailerons, which are flaps towards the end of your wings, whereas the inboard, you typically have flaps to enhance the lift during takeoff and landing. So, and various other phases of flight. And then the pilot has these rudder pedals as well, by which the tail, vertical tail, you will have at the end the control surface called the rudder, which can be moved left or right. If it moves to the left, the aircraft turns to the left. If it moves to the right, the aircraft turns to the right, because you're modifying the aerodynamic force generated on that, which if it were horizontal would be like a lift, but because it's vertical, it's a sideway force, and that's causing that. And many of these things will be coupled. And you will see in that, though we start off with a 6 degree of freedom system, 3 each will get decoupled. So essentially, whatever is happening in the plane of symmetry of the aircraft, that kind of motion, namely the horizontal flight, the vertical flight, and also the pitching motion, these 3 are coupled with each other. Then the rolling motion, the yawing motion, and the sideways drift that might be there, these 3 are coupled with each other. And so essentially, you're dealing with 2 3 degree of freedom systems decoupled from each other, and then you arrive at certain things. That's where we start our work. Then now we know, as flight vehicle structures engineers, what are the kinds of loads which are coming, overall sense of what is the lift that the wing is generating, how is it distributed along the span of the wing when certain maneuvers are done, or in order to maintain the stability, what kind of forces are generated on the vertical tail and the horizontal tail, how are they distributed on that, and how these are transferred to the fuselage. And then we design the inner structure of this. How is this whole wing made up of? What are the structural components which make it up? What are the fuselage components? How these 2 are attached to each other. Similarly, how the horizontal vertical tails are attached to the fuselage, how the engines are attached if they are on the wing or to the wing, or if they are on the fuselage to the fuselage or to the vertical tail. So all of these decisions are made by the aircraft structural designer based on the inputs that are given from the flight and space mechanics, who in turn receive inputs from the aerodynamics people, what you're studying as part of your fluid dynamics course. A lot of that will cater towards the better understanding of that in terms of estimating the loads. So to some extent, this load estimation is a joint activity between the aerodynamics team and the structures team as far as aerodynamic loads are concerned, between the propulsion team and the structures team as far as the thrust is concerned from the engines, etc. So you have this collaborative effort, and again, the controls engineers are the ones who determine in terms of what kind of deflections you have to cause what kind of increase or decrease in the forces generated by these control surfaces, namely the wing, horizontal tail, and the vertical tail, by deflecting your elevators, which you have here as we just discussed. So these are the elevators on the horizontal tail. These are the rudder on the vertical tail, and typically at these 2 ends you have the aileron for the roll. So elevator is for pitch and the rudder is for yaw. Of course, these are not independent. The aileron and the rudder have to be operated together in order to have the desired kind of motions in the out of plane of symmetry of the aircraft in order to have motions there. So this being the overall approach, it's important to understand not only the characteristics of the aircraft material, but also which materials goes into which structures. Typically, it's not a single material which goes into a particular structural component. It could be more than one, hybrid designs. So what is the reason for selecting a particular material, and what is the reason for choosing a particular shape and size of that particular structure is what we will look into as far as the characteristics of the aircraft material and structure are concerned. So once we understand that in a qualitative sense, in order to actually make calculations, most of these are operating in the so-called elastic limits. By a particular material being in the elastic limit, we mean that in the loading and unloading process, you're essentially coming back to the same state. In other words, your stress is a function only of the strain, so that there's no remaining strain or residual strain once all of the load has been removed. So whatever you started off with before applying the load, you end up with that after the load has been removed as well. So this is a area where it is much more amenable to simpler mathematical modeling techniques, and that is where most of the aircraft structural components are operating in most of the time. Within that strain limits, a certain maximum strain limit up to which the elastic equations are valid. So we will introduce elasticity from that perspective, and then probably I'll go into the next, because I'll not follow exactly the way the chapters are there in the case of the textbook, but we will try to do it in a slightly different way. So we'll start with the fundamentals of flight vehicle structures, and that includes the flight vehicle materials, which is what I just discussed so far. Then when we get into the introduction of to elasticity, most people do it from not only an elastic material, but another simplification they bring is that it is an isotropic material. In other words, the material properties are the same in all directions at a given point. Then they also make another assumption, what is called as a homogeneous material, whereas in reality you could have a heterogeneous distribution, which means that different materials at different points and therefore different properties at different points. So since composites are used for most of the aircraft structural design these days, and the trend is on an increasing side as we go forward. You know, for example, you have even in the transport sector, the public transport vehicles like you would say the Boeing 787 Dreamliner or the Airbus A350. These are two aircrafts which have used more than 50% of composites, and from the structural point of view, and that is going to become more and more. We haven't had a major large aircraft, wide-bodied aircraft design in a long time, but if there were to be one today or tomorrow, it would definitely try to beat that, because of the kind of advantages that those two designs gave to the entire ecosystem, be it the airlines which are operating those aircraft or the passengers who are flying those aircraft. Everybody benefits from these kinds of technologies. So when we introduce elasticity, we will of course maintain the elastic material assumptions, but we will relax the isotropic assumptions, and where necessary the homogeneity assumptions, and go to heterogeneous anisotropic materials which are composites, and see how they are analyzed. And the usual material, conventional materials used in the past, which are also used to some extent in various parts, even in Boeing 787 and the Airbus A350, the other 50% are non-composites, which means that most of it is metal, and that is isotropic in nature. So are you left with no way of handling that? No, not at all, because metals, at least within the elastic limit, become a special case of the composites. You just make the properties in all directions the same, and wherever heterogeneity is there, you bring in a certain level of averaging to bring in the homogeneity back. So you will be able to handle it. But once it goes beyond the elastic limits, metals become much more complicated to deal with because of the plastic deformations. Many of them yield, and then you could have permanent residual strains, whereas most composites are brittle in nature. So the way they fail is typically without yielding, and therefore from the failure analysis point of view, sometimes the metal has more complications compared to at least in the process by which it fails, and which is actually advantageous to some extent because of the fact that you know that you are getting into that failure, you have some time to get, whereas in a brittle failure, it happens almost all of a sudden. But in favor of the composites is the fact that many of these have such high failure strains or failure stresses that you probably don't need to look at this aspect if you have considered the proper levels of factors of safety, etc. it may not even be necessary unless you're doing research towards that or trying to push the limits, maximize this, make a better composite design, etc. So keeping all that in mind, it's not so difficult as it seems to introduce composites right up front in an introduction to elasticity study, because this is a course which is not going to replicate what is taught in civil engineering or mechanical engineering in parallel in this very campus in terms of a solid mechanics course which is going on there, which is a core course for them, very similar to the fluid mechanics that you're having. They have a solid mechanics course. But that solid mechanics course is going to into far more rigorous mathematics in terms of understanding the overall process of how solids behave under mechanical loading. We will not go into all those details over there. In other words, this is more of an applied structural mechanics rather than a solid mechanics course, and in particular applying it to flight vehicles and their structures. So that's how this will be done. So these two will pretty much take most of the course. The next biggest chunk of work will be on analyzing what are known as dimensionally reduced structures. In other words, if you look at the kind of building blocks that you have for civil engineering structure, typically these bricks that you have, of course today you have hollow bricks, etc. But essentially the dimensions, if you look at in all three directions, are of the same order of magnitude. They're not equal numbers, but you can't say one is like 10 or 100 times the other dimension. So that is a huge difference amongst many differences that we were talking about in the previous class in terms of how flight vehicle structural geometries are, structural component geometries are compared to the component geometries of a civil engineering structure. And typically you will be having either beams and or plates and shells. Plates like what you have this tabletop, for example, where the thickness of this tabletop is quite a few times the width of this, leave alone the length. So you see something like this. You would have even thinner shells in the case of flight vehicle structures compared to the length and the width of the plate. And most structures, as you know, whether it's the fuselage or the wing, etc., because of the airfoil section that is needed from the aerodynamic requirements, these are curved surfaces, so you no longer can have plates like this. You'll have to have what are known as shells. So these shells, again, are thin shells that you're going to be dealing with. Now, we will look into the specific construction philosophies, what are known as truss-like constructions. We will look at monocoque constructions, which is a French word. Mono meaning single and coque, C-O-Q-U-E, meaning shell, and like an egg, essentially. And we will look at semi-monocoque constructions, etc., where we'll be talking of skins which are going to be reinforced with certain longitudinal and transverse members. And many of these longitudinal members are in the form of what are known as beams. So essentially, what we are talking about now is very similar to the beams that you have in the case of civil engineering structures as well, where the cross-sectional dimensions are small compared to the length. Now that's okay as far as a static definition is concerned. Most of our beams in the flight vehicle are operating in the dynamic regime, so it's not enough for us if the cross-sectional dimension is small compared to the overall length of a beam. That alone doesn't classify as a beam definition for us, because we have to look into the dominant structural dynamic modes and see that compared to the wavelength, it is the cross-sectional dimension is small. So what you compare with in a static problem to see whether a beam model is valid or not is the cross-section compared to the length, whereas in a dynamics problem, you have to compare it, the same cross-sectional dimension, with the wavelength of deformation. And of course, there are many, many modes that the flight vehicle will operate in, and eventually the structural component will also operate in based on the kind of maneuvers, the various phases, even without maneuvers like landing, takeoff, taxiing, climbing, descending, and cruise, etc. All of those have to be taken into account within the flight envelope. And then, yeah. Yes, there would be. The most basic equations are typically what are known as asymptotically correct, and we will have those equations in place. But once we go on to more, the requirement of more and more accuracy, we will see that the regular things like what you use over here will fail, and you will have to use better ways of doing it. So that's the essential thing. So the difference is not coming more because of that is civil and this is aerospace. It is coming because of the kind of materials that you have, the kind of geometries that you have, and also the kind of loads. So in particular, what I was talking about just a few minutes back was the fact that we are now considering dynamic loads. So even in a civil engineering structure, if you were to consider dynamic loads as the dominant load for a particular structure, let's say you're doing a seismic analysis, or you're doing for a hanging bridge, you're doing some kind of an analysis purely from a dynamic point of view, there also what needs to be considered in comparison to the cross-sectional dimension is not the overall length of the bridge, but your essentially the wavelength of deformation. Only if that is a small parameter, a beam model will be valid. If it's not a small parameter, you have to go for a whole 3D analysis, which is much more computationally involved. Come again?
If you are designing every component here within the elastic limit, you are not stretching them up to the elastic limit,
It depends. So see, different components will be undergoing different stresses even in the same phase of flight. So depending on that, if you are talking of the material model and the same material is being used in two different components, yes, the same material model can still be used. But it depends on what level of strains this component is going towards, maximum strains, what level of maximum strains the other one is going through. One of them might be still within the elastic limits, the other might be crossing the elastic limit. So you need to make a difference based on what is the typical maximum levels that each one of them goes to. But you design it in such a way that because you want to minimize the overall structural weight, you will make it so that in such a way that there's not such huge difference between two structural components in terms of the strains that they face if they're made of the same materials. You would try to reduce the weight of that component by making it thinner, for example, which is not undergoing that large a strain or stress, because then you're obviously taking much more weight of the structural material than is necessary. Yeah. Anybody else? Any questions? Okay. So typically, lot of these reinforcements, be it the spars or we'll come to what exactly they are. Many of you from the aerospace background might know, but those from the non-aerospace, I'll talk about these in greater detail as we go forward. But essentially, these are components which make up a wing or a tail or the fuselage. So these components which are reinforcing the skin of these, there is a skin for the fuselage, there's a skin which is like our skin, it's the covering material that is there, which is also stressed in some sense, but it is fairly thin. It cannot take all the loads by itself for a typical large aircraft or a fast aircraft or both. So in such situations, what we have to do is we have to reinforce this, which is why we call it semi-monocoque. It's no longer a shell, but a reinforced shell. And that kind of design, all those reinforcements that we are talking about will typically be what we are calling as beams. When we talk of beams in a regular undergrad engineering program, we talk about beams as just the bending. So when a bending load is applied, we call that structural component as beam. But we will use it in a more generic sense. We will call any one-dimensional structure, like what we just defined, the cross-sectional dimension is small compared to the dominant wavelength of deformation of the beam, then we call it a beam. But the load could be either bending, or it could be transverse shear, which is the transverse forces that are there. If this is a beam, then this kind of a load or this kind of a load or at any angle, that is essentially causing the flexural shear. And then there is a twist, which is essentially trying to apply a torque to this, and therefore it is twisting. And all of these in general are possible for the wing and for the tails as well. These are possible under different situations. For example, a very simple situation, if I want to pitch the aircraft, I deflect the elevator, right? So if I deflect the elevator down, I generate extra lift over here, it pitches nose down. So what is happening over there is essentially, as far as this structural component of the wing is concerned, or the horizontal tail is concerned, it is generating extra lift, and so that could be generating a torque as well, depending upon where that resultant force is acting compared to the other geometrical locations. There are many parameters we'll introduce as we go. Certain concepts will be defined in your flight and space mechanics course, like the aerodynamic center, etc. Here we'll be talking of what are known as the elastic center or neutral axis, etc. And the way these neutral axis, etc. is defined is quite different from the way you would have studied in your basic strength of material course for bending, because once all of these are present, there are more subtle ways of defining it. Of course, the end effect is same in terms of the qualitative. What we think of as neutral axis is that when you are subjecting this to a bending, some portions of the cross section are going to undergo tension, some portion are going to undergo compression. So there is a line in between them where there is neither tension nor compression. It is under zero stress. We call that as the neutral axis in this direction. The same cross section could be bent in the other way. Then you have a neutral axis there, and the intersection of those is essentially taken. But once you bring in composites, things get a little more complicated, because when you're trying to bend it in this way, you're applying a moment like this. It could also be at the same time bending like this, even though you're not applying any moment like this. So how do you define the neutral axis in those cases? These are all things that we will touch upon towards the second half of this whole course. But rest assured to see that essentially from a pure mathematical point of view, these are all very similar looking structures. Cross-sectional dimension is small compared to dominant wavelength. So that is what we are talking about. And in terms of the load also, if you actually look at it, shear is essentially a force, and bending is essentially a moment. And a moment is caused by a force operating at a distance away from where you are experiencing that force. So essentially the source of it all is the same. And even if you look at torsion, it's essentially a couple, two forces of equal and opposite direction operating at a distance away from each other in terms of their lines of action, and that causes a torque. And in terms of how the material responds to it is also very, very similar. If you look at what happens when you're applying a transverse shear or let's say transverse load, then you're having transverse shearing stresses in the cross section. So similarly, when you're applying torque, also you're having transverse stresses, but just that they are going to change direction. Whereas in the case of a load, vertical load, you're going to have only vertical shear, even if it's an isotropic material. And if it's a torque, then you're going to have the angle changing even in an isotropic shaft. And those things, the shaft, the beam, the column, which is typically used for the compressive loading members, all of that we will lump together into a single term called beam, which is essentially a one-dimensional structure is what we are trying to see. So whereas in reality, all structures that you look at in life, be it in civil, mechanical, or aerospace structures, they're all three-dimensional bodies. But we are trying to take advantage of the fact that the thickness is small compared to the length or width. We don't need to deal with it as a 3D body anymore. Can we deal with it as a 2D body in this case? Case of the beam, can we deal with it as a 1D body? The mathematics gets much less complicated. Instead of dealing with, for a 3D body, partial differential equations which are having 3 independent variables, here you have only 2 independent variables. And in the case of the beam, you'd have only 1 independent variable, so it's no longer even a partial differential equation. It becomes an ordinary differential equation. So this simplicity helps us to do things much faster. And when you're doing it in a design problem, optimization is required. And this optimization process means running the same theory over and over again over a particular component for various cases of loading. So each time that you save, duration that you save, is going to add on, and which means that essentially from a business perspective, you're able to take your product to the market much earlier. So if your company has this way of approaching the problem as opposed to another company which does just 3D finite element analysis, which is also has its own place in different locations, depending on the complexity of the problem, then obviously your company is going to be able to take the same product to the market earlier. And this means a huge difference in terms of the marketability of the product that you're coming up with. So these are all the things which are driving forces, which most engineers are unfortunately not exposed to. You have to understand the overall dynamics of how the industry operates. Even if you are going to do pure research, let's say even in academia, eventually you'll be looking at funding projects and things which are coming from the industry. So it's important for you to understand how is the geopolitical situations, how they are affecting, for example, the Air Force and the Navy, what kind of situations are arising from the geopolitics, and how that affects the kind of usage that they're going to have, how that percolates down in terms of the requirements of the mission requirements, how those mission requirements eventually translate into the vehicular requirements, how those vehicular requirements translate into the structural requirements and then the material requirements. Do we have those materials in place? Do we need to develop them for a future need? And if you do have it, how do you organize or reorganize, arrange these in different ways so that you can offer the most effective solution that is possible with today's technology? So this is essentially a process that one needs to understand, irrespective of whether you are from an aerodynamics, controls, or propulsion background, doesn't matter. You need to understand, these basic qualitative elements and a little bit of math that goes into that. And that's essentially what we will try to cover here. And because of the weight requirements, most things that you'll be dealing with are thin structures. Be it the plates or shells, it will be thin plate, thin shell. If it is a beam, it will be a thin cross-section beam. And once again, depending upon whether it is prone more to torsion or it is prone more to flexural shear, you would have either a closed cross-section, open cross-section respectively. Why that difference, etc., we will see. Even the simple mathematics that we go through will give us an insight into why those choices are typically made. So that's what this will entirely cover. And there's an abbreviation I'll use quite often, cross-section, to just keep things compact on a slide. So open or closed cross-section beams is what we are talking about. And it's not that like how we study in strength of materials, particular component will be subjected only to torsion, particular components will be subjected only to bending and shear. Here, you would see in real life, all of them are going to be subjected to all of these loads, and maybe even the axial load, especially when you're talking of helicopter rotor blades, because these are rotating members, the centrifugal force is going to be one of the dominant forces apart from the lift and drag forces that are going to be generated. And that's also a distributed force, the centrifugal force. And that's an axial load as far as purely as a structural engineer when you're looking at it. What is it? It is essentially an axial force which is varying along the length of the rotor blade. So you would, and those are typically what are called as in most conventional courses bars. So you call anything undergoing tension as bar and anything undergoing compression as a column or strut. And if it's a string-like thing, you call it as a tie instead of a bar. So all of those will be clubbed into our definition of a one-dimensional, generalized one-dimensional element. Similarly, whether it's a plate or shell, it's a generalized 2D element that we will be talking about. We will be generally mentioning it as a shell. Whenever it becomes zero initial curvature, it becomes a special case, it becomes a plate. So the plate and shell equations are a little more complicated. Still, we are dealing with partial differential equations. So it will be beyond the scope of this course to look into them, but we will have certain glimpses of it because a large part of the flight vehicle structures are shell-like structures. The skin of this entire fuselage, wings, the stabilizers, they're all essentially you are having a shell-like structure, in fact, a thin shell. And many of these concepts that we're talking about for beams, many of them will be valid for the shell also in terms of how it actually operates, and we will look into that. In fact, we have an advantage because we are introducing composites at this stage, because the way the composites are built is in what is known as a laminated structure. In other words, there are plies Each layer will have certain composite layers which are typically very thin, of the order of, let's say, 0.1 mm or a little more. So now you have stack up many layers in different directions as far as the fibers are concerned, because in that particular structural component may be undergoing loads in different directions, and to be able to cater to those requirements, you cannot have all the layers having fibers only in this direction parallel to my fingers. So you will have to have the fibers in different directions, because composites are stronger and stiffer along the fiber direction compared to the direction perpendicular to it. And why and what the reason for that is quite intuitive, but we will look into the mathematics of that as well as we go into this portion of it. So that's as far as torsion, bending, and shear is concerned. Before we get into this, again, as I said, this is as far as the structural component is concerned, and how the load is getting transferred either from the aerodynamics and or the propulsion and or the control systems onto the particular structural component through other structural components that it is joined to. But in terms of how the material responds to it, that's where the stress comes into picture, the strain comes into picture. These are all the reactions of the material to what is being done to it. And that is also again very, very simple in terms of the stress. If you're looking at just basic two kinds of quantities, normal stresses and strains, and you have the shear stresses and strains. So torsion will predominantly be causing your shear stresses and strains. The transverse load will also, by its very name, causing shear. The bending will typically be causing your axial loads, very similar to what axial loads cause in a bar or a column. They will be causing tension and compression, which are normal stresses. So normal stresses and shear stresses. But is this torsion always going to be shear? Is there a possibility of torsion causing normal stresses? Anybody? You say bending causes normal stresses is understandable. You are trying to apply a bending moment. So the top layers will undergo compression if the direction of bending is like what I'm showing, indicating over here with my hand. Then if you're, the bottom ones will be undergoing tension. So it's quite clear that normal stresses are being created by it. Now I'm applying a torque on this cross section. Essentially it is going to be shearing in this direction as well as this direction. Is it possible for torsion to cause, apart from shear stresses, is it possible for torsion to cause normal stress? This is what I'm asking. Very good. So that's the key there, that you should be very important in qualifying when you say stress, which plane you're talking about. So the same point you're discussing, in one direction if you see it might appear like shear, and in some other direction it will be a normal stress. And that is probably very easy to illustrate. So suppose you think of this as a torsional shaft, and you think of a fiber which is running, let's say, 45 degrees to this. Now if I try to twist this way, you see that this fiber will actually become lax. In other words, it's undergoing compression, which is why it is becoming lax. On the other hand, the same fiber, if I put it in this direction at 45 degrees, you will see that, and I am twisting in the same direction, then you will see that it is getting tense, it's getting extended. So in other words, both of these are normal stresses which are coming because of a reaction to a torque. So it's wrong to say that torque always produces shear. Yes, that is the main thing if you're looking at the particular cross section in which you're looking at it and the directions in which you're looking at it. But at the same point, you know, more circle, for example, which you have used so much for gate, etc. So you would see that a same stress state, which is a pure axial load, can cause shear at an angle 45 degrees away from it, from a plane. And any in-between planes, not 45 degrees, not so sacrosanct, you would have both of these being present. Even though you have a pure tension compression that you're talking about in one direction, you could have combination of tension, compression, and or the shear that is happening in the different directions. And the same thing holds as far as bending is concerned. We normally say bending causes only tension and compression, but depending on the direction in which you look, you could have the other kinds of loading happening as well. So just be a little careful in dealing with that, because we are going to design these components out of composites, and therefore the direction which you put the fibers, etc., become very, very critical, and you need to start thinking about how the different stresses which are normal in one direction become shear in other direction. Are you having enough fibers to take care of that? All these kinds of decisions will depend on that. So it's very important. These are all very basic concepts that you have already learned from principal stresses, principal strains, and then the Bohr circle, etc. But now we are in an application mode. We are looking at an actual aircraft structural component. When you're designing with a particular material in particular composites, what are you trying to make this decision out of? Now, one thing is the choice of material, where we talked about the parameters in the previous class itself, specific strength, specific stiffness, etc., and specific stability. But once you've chosen the material, how do you actually orient it? All these things becomes very critical, and how many layers of it you have, and in each layer, what is the angle, and which layer you put on top, which layer you put on bottom. The arrangement becomes, so it's not just a combination, but a permutation as well. So the ordering arrangement becomes critical as well. So that's as far as the components are concerned. And individual components, whatever name you give it, spar, stringer, longeron, rib, the bulkhead, or the former, etc., doesn't matter. Essentially, at the end of the day, these are all structural components. You're applying either forces and or moments. Some forces are like shear in particular directions, but in some other directions they are axial loads, etc. Somewhere they cause tension, somewhere they cause compression, and how they respond to that stress strain, that is what is important. And then you try to stretch the limit, because in the design you want to make sure that you're not carrying dead weight, you're not carrying more heavier than what is required beyond the factor of safeties that you have already taken care of. Then you need to understand the failure process. Then the failure criteria come into picture, what is known as Sai criteria, Sai Wu Han criteria, etc., which special cases of which are applicable to metals like Tresca and various yield criteria, etc. So we look at those. Then the fracture aspects, I don't think we'll have too much time, but we will touch upon it. And fatigue, because most of these are loaded in a cyclic manner. So in other words, stress is changing, and it is changing with respect to time in a particular periodic manner, and therefore the stress or strain with which it would have failed in a static case, in a static loading case, at a much lower stress or strain, it would fail because of this time varying load. And even if it is not periodic, the kind of motion can be broken up into periodic parts. You know what is a Fourier series expansion, for example. You can break it up into parts, and then there's a way of summing over it and seeing whether it would fail by fatigue. So that's another thing we will, as I said, these ones in yellow, we will not cover it as separate topics. We will incorporate certain aspects of it when we are discussing these things. These would be the topics that we would be covering in the course. Next is many of these structures are subjected to compressive load, and because of the compression, there is a possibility that material still has not failed, but the way the geometry of the structure is, there is a certain instability which sets in, what we call as elastic instability, because we are still within the elastic limits, and that elastic instability is typically called buckling. And that can extend to what are known as aeroelastic instabilities like divergence or flutter, etc. All of it beyond the scope right now. In fact, this semester there's another course going on aeroelasticity. Your MTech courses, you have your MTech students, you have your hands full. You'll probably be not able to take that now. But those of you who are in the structures field who are interested in that, maybe in the third semester you'll be able to take that particular course. But essentially the concept is very similar, that an instability is happening. Material is still okay. It has not crossed its failure limits, but still the structure as a whole is failing. And this is because of an instability that is setting up. Again, we will not cover that as a separate topic. It is there in your textbook. For those of you who are interested in reading it and discussing with me, you're most welcome. But we will cover certain aspects of it when we are dealing with compression over here. Because again, as I said, it might look like you are not applying any compressive load to a particular structure, but it still might be buckling, because in some other direction that load that you're having is causing compressive load. So let's go back to the simple example of that shaft under torsion that I was talking about. We saw that one of the fibers at 45 degrees, depending upon which direction I apply the torque, can undergo compression, and therefore in that direction there is a possibility of a local buckling that is happening. When the structure as a whole is loaded with a compressive load, then the structure as a whole could buckle, and that buckling, most textbooks that we read in undergraduation will only talk about a possibility of buckling in this way in the direction of an imperfection and or some eccentricity in the loading, etc. But that is one type of buckling called flexural buckling. That is buckling by bending. If the bending stiffness at some location is below par, then that can happen. But the same compressive load can sometimes cause what is known as a torsional buckling. So in other words, if the torsional stiffness is very low, for this I am applying a compressive load, even before it undergoes flexural buckling, it can undergo torsional buckling. So that is another concept which is overlooked, and this should not be overlooked, especially for aerospace structures, because you have thin open sections. Whenever you have a thin open section, it could be a channel section, it could be an eye section, etc. It has very good bending stiffness in particular directions, but the torsional stiffness is very low. Whereas for a closed section, when the dominant load is torsion, you would mostly use closed sections, or you would use components which are joined to each other to make a closed section, what are known as wing boxes. So if you take an airfoil cross section, you would divide parts of it into structural members such that you have what are known as wing boxes, and each one of those boxes has multiple components but acts as a whole because of the way it is joined to each other, either using adhesives or rivets or bolts, countersunk, whatever you have. But essentially what is happening is it's operating as a team, and because of that it's able to take the torque as well. But the fact is that even when you're not having a torque but having a pure compressive load, if you happen to have an open section which is thin, then there is a possibility that it undergoes torsional buckling. So we will look at certain concepts of that without going into the depth of the mathematics that is involved over there. And finally, the other things that are there in your book as well are structural dynamics, which is very essential. As we discussed in the previous class, one of the primary differences between civil engineering and the aerospace is that you have vehicle structures, which means that you're dealing with dynamics more. But the advantage is that even when in a dynamic problem, that is when there are time varying loads, you will see that the problem breaks up into two parts. One part is about the smaller dimensions, which is in the case of a beam-like structure like this, it's the cross section. And there is a larger length part, which is along the length of the beam. So even when you're loading this in a time varying way, the dynamic way, it will be such that the dynamics does not to a large extent affect the cross-sectional analysis. It affects only the what we call as the 1D analysis, or the analysis along the larger dimension. Same thing as far as this plate or shell is concerned. You could have a dynamic load operating on it. It could be a fatigue, it could be an impact, it could be a periodic sinusoidal loading that is happening. Whatever it is, essentially there is this problem. Instead of a 3D problem, it will break into two problems. One is a 1D problem through the thickness. Along the thickness there is one problem. Then there is a 2D problem. I take the mid surface or some reference surface of this. It could be the top surface, bottom surface, mid surface, or any other surface. There I am dealing with zero thickness element, and that's where, because it's the larger dimensions, the dynamics will operate. Is this an assumption? No. Mathematically, rigorously, it can be proved that when a 3D problem, either for a plate or shell-like structure or for a beam-like structure is applied, you would see that as we bring in the fact that this is of one particular dimension is either very small compared to other two dimensions, or one particular dimension is very large compared to the other two dimensions. Once we take advantage of that, the problem will automatically break up into two parts. One is along the smaller dimension. The other is along the larger dimension, which in this case is a 2D problem. So when that breakup happens, all of this, what you have done here, considering pure statics, is still valid as far as the cross-section of a beam is concerned, or through the thickness of a plate or shell is concerned. All of that is still valid. So it's not a waste, even though it's very simple. We are not looking at time-varying loads up to this point of time, and this involves time-varying loads. Is all of this not going to be used here? No, it is usable as far as the smaller dimension is concerned, but for the larger dimension, you have to develop the second independent variable as well for a beam. You are very happy that the beam has reduced from a partial differential equation problem to a ordinary differential equation problem with only independent variable being along the length of the beam. But no, once this comes, your time becomes another independent variable going back to a partial differential equation. But still you have a huge advantage. Instead of dealing with 4 independent variables, now you're dealing with only 2 independent variables. So you have much simpler partial differential equations to deal with, and the solution process are much more effective. Then we have a very good testing facility in our department, both for metals as well as composites. The universal testing machine we talked about in the previous class. There are many other very intricate testing methods, including non-destructive techniques, be it ultrasonic or many other X-ray, etc. So all of that is possible here. So many structures specialization students typically do their project in those areas as well. As I said, aeroelasticity, there's a course going on. There are also tunnels in which tests are done with respect to aeroelasticity. So both the theoretical as well as the experimental work on aeroelasticity is possible. And then this has become kind of the bread and butter of most structural analysis. Eventually any complex structure, complicated either from the material point of view and or the geometry point of view, eventually you will have to depend upon a numerical technique known as the finite element method, where you're breaking it up into small parts. Once again comes back from the same philosophy that we are talking about. Instead of the wings generating both the lift and the thrust, we broke it up into the wing and the engine, giving 2 parts. Then within each structure, we broke it up into the skin and the stringers, which are reinforcing it. Then each one of those components, when we want to analyze, we further break it imaginatively into elements separated by nodes, and that's essentially what we apply that technique called the finite element method. So once we are done with that, we'll have certain parting remarks. Most people call it conclusion, but I feel that the word conclusion is very unfair, because nothing can ever be concluded, especially in science. Things are always on the move. You go to better and better things. So by the time we conclude this course, we'll have certain parting remarks in terms of what kind of state of the art we have learned and what are the future trends in terms of how these things will change as we go forward. So this is essentially what we will cover here. Probably have a few more minutes. Let me see. Maybe it's good to stop here, because a new topic will be taken up in the next class. As you know, you might have seen one board over here, which is essentially an interactive display board that has been shifted. Since most of you are having classes in 105, you would have seen it over there. So that more instructors can use it. So since that will be kind of much more useful than a green or blackboard for me, I will also be shifting my class to there. I found out that there's no clash with any other course happening at that time. So Monday, of course, is Independence Day. So next Friday when we meet, we will meet in 105 and continue the course. So as far as the class is concerned, I'm done today. So any of you have questions, you're free to interact with me next few minutes.
During torsion, you told that one of the fiber will have compression element.
Yeah. Can I?
Is this only applicable for composite? If the material is high
No. I'm using the word fiber in a sense that it just take any material element. So I could be talking of a metal shaft. So I'm just talking of the loci of points which are at a 45-degree plane. So essentially we are talking of a spiral. So it need not be 45 degrees. 45 degrees it is maximum. But any angle other than 0 degrees when you take a set of material points, you would see that depending upon the direction in which I apply the torque, either this direction or that direction will undergo compression, the other one will undergo tension. So this is very simple from your Morse circle point of view also. You know that you typically plot the shear stress versus the normal stress. And if you have a Morse circle which is centered on 0, 0, you know that at a particular location you have pure shear. But if you look at just 45 degrees away from that, which means here you have to take 90 degrees, you would see that you would have minus sigma naught and plus sigma naught, which we call this as tau naught and minus tau naught. Then this sigma naught is equal to, in terms of magnitude, it is equal to tau naught. But now you're talking of a tension in this plane and a compression in this plane. So that's essentially what we are talking about. And that's very simple to see. You can just take any rod which you can easily flex like an eraser or whatever. You just put a thread over it and try to turn it. You will see that it is getting extended if you twist it in this way. And if you twist it in this way, you will see that that becomes starts lagging, which means that it's trying to be compressed. Right, so just for illustration, I talked about a fiber or a thread, but this is something that happens irrespective of the material. Need not be a composite.
So in the case of pure bending, say when we have made pure bending, so can the compression due to bending be large or something?
Yeah, so we talk of the buckling of the whole structure, that is called as global buckling. What you're talking about is what is known as a local buckling. So there's a possibility of a local buckling or what is also known as wrinkling in the case of skins. Okay, so that is something that happens in a local region. In this case, you're talking about those parts of the beam which are undergoing compression because of the bending that you're having, and it is possible for that to buckle as well. Yes.
Only the top fiber can.
Exactly. Yeah. Because you usually do not have a solid construction. What you will have is a hollow construction. So it's like a box beam, let's say. So essentially it's made out of 4 walls. All of which are thin. Okay, and you are subjecting it to a bending moment, let's say M, that we call it. Okay, so if I introduce, let's say, along the length of the beam, which is perpendicular to the board, is x1. So I call this as x2 and call this as x3. Then this is about M2, so it's about x2, so we can call it as M2. So which means that it's essentially a moment like this, which is it's a negative value because it's opposite to the direction of this. So now you see that the bottom phase is under tension, but the top phase, top sheet of the top wall of the box beam is under compression. So it's possible that if the M2 is increased beyond a certain point and still the material has not failed, then it's possible that this undergoes what is known as local buckling. So local buckling is very much possible under such a situation. And typically, of course, you will have reinforcements in different directions, because of which it could be retarded. So there are engineering ways of avoiding it. And as far as the skin is concerned, sometimes you allow it to buckle and still operate the aircraft. There's absolutely no problem because it's not a material failure, it's pure geometric failure. And there are other elements which can take that load. Once the skin has buckled in a particular local region, the rest of the stiffeners will take that load, and you are allowed to fly safely. The aircraft will be certified even for that. So there's no issue with that, but you should be aware of that phenomenon. Because once the skin is buckled, you have to design your other reinforcing components to take what lower load was taken by the skin earlier, now has to be shared. That additional load has to be shared by those reinforcing members. As long as they've taken care of that, no issues. Okay, so thank you then. We'll meet next Friday. Wish you all a happy Independence Day.